Scientists have now performed an MRI on a single atom, the world's smallest MRI. How cute is that? This level of resolution is a breakthrough for the world of microscopy and has potential applications in all kinds of fields, from quantum computing to drug development. MRI stands for magnetic resonance imaging, and though it may be able to see things inside your body on the more macro scale, this picture is actually the result of tiny shifts in your protons. As the name implies, an MRI scanner creates an extremely strong magnetic field around whatever it's trying to image. This temporarily realigns the protons in your body with that magnetic field. Then the machine pulses the sample or the patient with a different current, a radio frequency, which pulls those protons slightly out of their alignment with the magnetic field. After the brief radio frequency pulse is over, the protons snap back into alignment with the field, kind of like a rubber band that's stretched between two fingers, snapping back into place after you pull it. The energy that's released as the protons move back into place with the magnetic field is what's detected and visualized by the machine. Different tissues are distinguishable from one another because their protons can take different amounts of time to snap back into place and release different amounts of energy when they do. But that's on the scale of the human body, full of protons. So how do you take something like that and apply it to a single atom? If you immediately pictured a tiny miniature version of an MRI machine, you're not alone. I'm right there with you. But no, that's not how it works. Instead, the researchers who created this technique altered an existing microscopy instrument, a scanning tunneling microscope. STMs involve bringing the tip of the microscope into contact with metal atoms at the surface of a material. The electron cloud of the atoms on the tip of the microscope interact with the electron cloud of the atoms on the surface of the material. When voltage is applied to the tip, those electron clouds become connected by an electric current. Then the electrons in the atoms of the material quantum tunnel to the tip of the microscope, giving you a pretty beautiful picture. This kind of imaging is highly detailed and at its best gets down to about 0.1 nanometers, or an angstrom, which is definitely atomic scale. But there's only so much information an image like that contains. Enter the atomic scale MRI. This joint research team from several institutions around the world applied iron atoms to the tip of a scanning tunneling microscope, generating a magnetic field. Further application of a radio frequency then induced changes in the spin state of the atoms in the material. The difference in spins between the tip of the microscope and the sample material gives us a picture of the atom. This means big things in the world of tiny science. The atomic MRI can image atoms on a sub-angstrom level, smaller than ever before. It can also tell us about their magnetic properties and spin structures, which you might imagine could be hugely useful in quantum physics, particularly quantum computing. This kind of computing relies heavily on the spin dynamics of particles, and being able to understand and potentially even organize individual atoms with this technology could drive unprecedented advancements in quantum tech. Atomic scale peeks at magnetic properties of molecules might help us with science on the nanoscale in fields like biology, too. This new technique may help us see how proteins fold, something that could lead to the development of better medicines. And while it's very exciting to think about the possibilities of this new tech, it's not the most easy to use apparatus as of yet. The microscopic MRI uses an ultra-high custom vacuum, requires cryogenic temperatures, and has so far only looked at very specific kinds of materials. But the researchers hope to keep developing their tiny MRI to be even simpler to use, continuing to see even more than ever before. If you have another technology you want us to cover, let us know over on Twitter and Instagram. We're @Seeker, and I'm on there too, @MarinB. Thanks so much for watching, and I'll see you next time.